Phil trained as a geologist and worked for a long time at the National Oceanography Centre in Southampton. And following that, he set up a commercial consultancy in Romsey, focused mostly on marine matters. But tonight he's going to talk about something that you will have seen in the news. You may have wondered with the name rare earths. And so he's going to inform us tonight on what are they, give us some facts, and also perhaps explode some of the myths about rare earths. So, Phil, over to you.
Okay, thank you, John. Where's my slide? Thank you, everybody. So I talked to Bill earlier in the year about giving this talk, and I thought I knew a little bit about rare earths, but when I spent the summer looking at lots and lots of publications on rare earths, I realized just how little I knew and what a big field it actually was. So I'm going to mention uses a little bit, but I'm not going to dwell on them, and it would be a topic for another talk because there's such a fascinating discussion could be had about uses, but it's not really my field. So what I am going to talk about is a little bit about the background to rare earths, the geology, where they're found, how they're mined, a little bit about the environmental aspects, and quite a lot about the economics, which is really why they're in the news so frequently. And along the way, we'll maybe explode a myth or two about them. So to start with a bit of a complicated side, except for the chemists in the room, this is the periodic table, and the row in colour, second up from the bottom, are known as the lanthanide elements. And these have atomic numbers of 57 to 71, and there are 15 of them. In addition, there are two other elements with very similar chemical properties, and they're known as scandium and yttrium, and they're put up there, and together they make the rare earths. So they're color-coded here, the left-hand side, the left 7 on the bottom column and the top one on the left are known as light rare earths. They have the lighter atomic numbers, and the others are known as the heavy rare earths. This is quite a fundamental distinction, so just bear it in mind. They fall into two halves, light and heavy, as we go through the talk. So rare earths were first found in 1788 in this quarry in Göteborg in Sweden. It does have a Swedish name, but my Swedish stepdaughters fall over laughing when I try to mention it, so I'm going to call it the English Göteborg. They were found in 1788, and by that time a lot of the elements were known in the periodic table, not all of them of course, but quite a few. And so they were called rare because they hadn't been found before, not for any other reason, or even because they are rare, because cerium, one of the rare earths, is actually more common than copper. So that's exploded one of the myths. and secondly, they were called earths because these were rocks that could be dissolved in acid, so typically metals were earths at that time. So the first one that was named was yttria, or yttrium, and that was named in 1794, as you can see. So what are their unique characteristics? Well, they have these unique magnetic and phosphorescent catalytic properties. They radically boost the magnetic strength, maybe from 12 to even 18 times that of an ordinary iron magnet. And magnets can then work at a much wider range of temperature. They have very high melting and boiling points. They have a subset of F electrons in their composition, and that gives them all of these properties. And they're also luminescent as well, and they are all metals. So they're known as the seeds of technology. Because they make today's emerging technologies possible. They're quite fundamental to many things we do, as we'll see in a few minutes when I tell you about some of the uses. So they allow us to miniaturize electronics because those magnets can be so much stronger, they can be that much smaller, and we need only a small piece of them. And they typically enable a lot of the green technologies and a lot of new medical technologies that we use today. And they are very fundamental to defense industries, telecommunications, and transportation systems. So a little bit about the geology. This is one of the rocks that they are typically derived from. This is called a carbonatite. It's a very peculiar rock. It's not very common on the Earth, and that's probably why rare earths are not found so commonly. I said cerium was as more common than copper, but in fact copper can be aggregated quite frequently into mineable proportions, whereas most of the rare earths are quite widely distributed and are not so easily found in mineable proportions. This weird rock has a high amount of carbonate minerals, and it comes from the mantle, which is very odd because carbonate is relatively light material, and the mantle is usually made of very heavy, dense minerals. In here, the white is all calcite, the green is olivine, and the black is magnetite. So an odd combination of minerals. And these have often been thrown out of the mantle many, many millions of years or hundreds of millions of years ago, and they have then gone through a whole process of change through metamorphism and various other processes to actually form the rocks which are the source of the rare earth. One of the key ones from this is basanastacite. So this type of origin covers about 62% of the rare earths that are currently mined. Another one is monazite, and this is commonly found as a gravel, just, you know what gravel is. Typically in India, these are placer deposits. They formed on beaches or on the sides of rivers, and they probably derive from some of that previous basastanite and other rare earth elements. There's another type, alkaline igneous rocks. It's another odd type of geology, and it's a bit related to the carbonatites up there. They're very high in sodium and potassium, which makes them a bit peculiar, and they're now known to have rare earths as well. If you look on here, it mentions that the carbonatites and the placer deposits provide light rare earths, and the alkaline igneous rocks can provide either or sometimes both. The only other type of rare earth that we currently have in production are these iron absorption clays. These are formed in quite a different way. Typically, a granite will lie in a tropical area where it's warm and humid, and as the granite weathers, its rock turns into components of the soil, and within that soil, the rare earths might be leached down into this layer in the middle. Is there a pointer on here? Into this sort of layer down here, and where they will accumulate. And as more and more granite erodes over many tens or millions of years, tens of millions of years, then this deposit can become quite widespread in these type of rocks. So that's iron absorption clays, and these typically contain the heavy rare earths. So this is the main source of heavy rare earths at the moment. So if we look at the composition in each of these types, the basastanite, the monazite, and the iron absorption clays, we find it's often quite different. So the three on the left, remember, are derived from the carbonatites or these alkali igneous rocks, and you can read the scale pretty much up from the bottom. So they contain a lot of lanthanum, a lot of cerium, praseodymium, neodymium, a little bit of samarium maybe, and then they start running out in those three on the left-hand side. But in the iron absorption Ks, it's better to read this down from the top. So they contain lots of yttrium, lutetium, ytterbium, thulium, etc., and not so much of these. So in other words, they're not entirely mutually exclusive, but one type of deposit has a majority of light rare earths, and the other type of deposit has a majority of heavy rare earths. And that's quite important as we go forward through the talk. So they're called, that's where the division is between heavy and light rare earths that I showed you earlier, and you'll see that it's not exclusive, but there's a dominance of one in one type and a dominance of the other in the other type. So typically, when you have a mine, most of what you're mining is just rock that you don't want, and the metal is incorporated in, copper could be 3, 4, 5, 7% sometimes. Rare earths, for those on the left, the basustanite and the monazite, they contain about 6% in Bayan-Obu. Bayan-Obu is a Chinese mine which supplies about half the world's rare earths. And Mountain Pass is the American mine, which I'll talk quite a bit about later. That has about 7.7%. So it's quite reasonable proportions. But when we come to the ion absorption clays, they're way down in the proportion of rare earths that's in them. 0.05 to 0.2% rare earths. So most of what you mine is just waste material. So I'll provide a little bit of their uses so that you know why they're important. So I mentioned before, permanent magnets. The strength of the magnet is hugely increased by adding rare earth to the metals that you're making the magnet from. And that enables the magnet to be much, much smaller in size than it would have been otherwise. They can work in a much wider temperature range than before, and they have a much greater resistance to demagnetization, so they will last a lot longer and in more adverse conditions than non-rare earth magnets. So these are particularly important for cars and buses and trucks and new types of electric vehicles. They're also used extensively in the wind power industry and in consumer electronics. And I've listed here the rare earths, but I won't read them all out. So a typical neodymium ion magnet, as used in wind turbines, can consist of 60% iron, 65% iron, 32% rare earth metals, 2% cobalt, and 1% boron. So 30% rare earths is quite a lot of rare earths in some of these magnets. And these rare earths that are used here, the neodymium, praseodymium, dysprosium, and terbium, they make up about 20% of the production by volume, but about 80 to 90% of the market value. So they're the key ones. Excuse me. Catalysts is another important product using rare earths. They increase the speed of chemical reactions, of course, and have a wide range of applications, particularly in internal combustion engines where they're used as catalytic converters, which you all know about in the exhaust system. So a range of rare earths again, using light and heavy. Polishes, this was a surprise to me, but they're very important in polishes. They give glass and mirrors their shine and prevent them from fading with time. So they're particularly useful in car windscreens, mirrors, optical lenses, and other glasses, etc. Metal alloys. So there's numerous areas of application here. They often play an important role in increasing the strength of these, such as in magnesium and aluminium alloys, which are used a lot in the airplane manufacture. And that enables, by increasing the strength, you can cut down the thickness of the metal and reduce the overall weight. So they're quite important in those areas. Batteries, not used so much as they were, but they were essential for nickel metal hydride batteries, commonly found in older hybrid vehicles. And I think this is the final one, glasses, where they're used in, the glasses used in space travel, where they cut down UV light, in touch displays in cell phones, lenses in eyeglasses, etc. They can be used to color and decolor glass and absorb the UV light, as I said, and in the laser industry, they're also used. So there are many, many uses. I haven't listed by any means even a small fraction of them here. Oh, ceramics is another one. These improve the properties such as resistance to heat and physical stress, and they're typically used in medical implants, and fuel cells that use hydrogen. So probably if you've got implants in your false teeth or implanted teeth, then you've probably got rare earths in your mouth at this very minute, or you've got a replacement knee or hip or whatever, then you'll have some rare earths inside you. Lighting, they're used to ensure that blue light is emitted by light-emitting diodes and converted into white, red, and green light, so they're very important in all these fancy new lighting systems that we have and use. So you've probably also all got a mobile phone in your pocket, and this is where they are likely to occur in that mobile phone. So in the screen, you're likely to have lanthanum to enhance the color and clarity. The speakers and vibration parts will have neodymium, praseodymium, gadolinium, because they've got magnets in them. The vibration unit will use dysprosium. 5G technology uses erbium, and the camera module will use neodymium and dysprosium. So a range of different rare earths, all there in your mobile phone. So when you dispose of your mobile phone, think about that it might need recycling. So what is the demand by use? And I came across two papers here separated by 5 years in time. So I put them on the same graph, and you can see there's been a big change with time. So that's roughly the order in which I just presented them to you. Magnets, first of all, is now by far the most common use of rare earth elements and is increasing rapidly. This is the percentage of use of each of these rare earths. So it doesn't mean if they've gone down on here, they've actually gone down. It means their percentage has gone down, which may be because the use of magnets is shooting up at high speed. But you can see with time that catalysts, the use in catalysts is actually decreasing, and that's because we're getting rid of the old ICE cars and replacing them with electric cars, and cars using catalytic converters are being made in lesser numbers with time. The others are relatively the same, except for batteries, because that type of battery is now not used very much anymore. So if we look at a couple of actual elements, dysprosium oxide, and look at the demand by sector, and this is a projected demand up till 2050 on the bottom here, you can see that the big expected growth is the third one along, which is electric vehicles. We're really expecting a massive uptake of electric vehicles in the next 20, 30 years or so. But the fourth one down on there is electric bicycles, which is quite interesting. It comes in on here and is expecting quite a rise with time. And that's probably because of China and India, which are massive, massive markets, and the bicycle is quite an important method of transport there. But all the other things as well, most of them are increasing. The interesting one on here, which isn't increasing much, is offshore wind, and that's probably because a lot of the capacity for offshore wind is being taken up, and there isn't huge capacity in countries such as China and India. Similar answer for looking at neodymium. Again, electric bicycles, but particularly electric vehicles really taking off, or expected to in the future. So the demand for rare earths is going to increase quite dramatically as we go forward in time. So what are the issues? You've now had your grounding in rare earths. You're all rare earth experts. So what are the issues going forward? So here are the two elements that come from carbonatite again, bastnasite and monazite. And when you have a mine, you dig a hole in the ground, and this time they're both rock, or similar gravel and rock. You mine the hole in the ground, and then you've got to concentrate that down, and then you've got to get the metals out. So the first step is called benefaction. This is where you grind that rock down into a certain size, and then you float it. So you put it into liquids which have a density such that the metals float off the top or sink to the bottom. I don't know which way around. They use maybe different flotation types for different ores. But it's usually flotation, and you concentrate, you get rid of some of the rock and you concentrate down the metals somewhat. And then after that, you end up with rock and metal mixed, concentrated up from what you had before, and then you have to crack it. And this is where you might use flotation and acids and roasting of that material. So a whole range of acids might be used in the production of the rare earth salts. And when you get the rare earth salts, they're all mixed together. So I haven't gone through the next stages on here, but your job then is to break them all apart into the however many constituents you've got from that mine, maybe 8 different rare earths or 10 different rare earths in that mine. Each one has to go through a process to remove it from that rare earth salt that you've got there. So there's a lot of work to be done when you've dug your hole in the ground to get the actual metal out. But when we look at ion absorption clays, these are quite different. These are absorbed onto clay minerals, quite loosely absorbed onto clay minerals. So with a relatively minor amount of work, they can be precipitated, driven off those clay minerals and released. And it's usually done with ammonium bicarbonate, and that will give you the same process. So it's a lot cheaper to go this method than that method, and a lot easier to go this method than that method. And that has consequences, as we'll see in a minute. So this is about pollution. This is what was the biggest mine in the world for a long time, the Mountain Pass mine in the USA. You can see the hole in the ground where the rock is taken out, and then it's carried up to the processing plants, the crusher, water treatment, etc., a whole series of different plants. And then eventually you have to deal with all these fluids which come off when you've done your cracking and your processing of individual metals. You end up with a lot of fluid, and you've got to get rid of that. And you also end up with all that waste rock. That's all got to be got rid of as well. And remember, I said these are about 6 or 7% rare earth, so you've got 90-odd% rock still to get rid of from that hole in the ground. Now, it turns out that the Mountain Pass mine was not very honest about the fact it was having a lot of leaks onto the Mojave Desert floor. And before the EPA caught up with them in the 1990s, there were about 60 leaks that happened, each one releasing radioactive waste onto the floor in the Mojave Desert and causing massive amount of pollution out there. So they were fined quite heavily in the end, and because they were being fined and it was becoming a problem, and they were looking maybe to reduce their output, the brother of President Nixon, I don't think he was the president at the time, but he suggested to the company, why don't you get all your metals processed in China? So just mine them out of the ground here, send them to China, they will process them, they can get all the pollution, and then we'll just get back the rare earths. So there was some opposition in Congress, but eventually it happened, and all the rock was sent to China for processing and then brought back. I'll give you a bit more detail about the Mountain Pass, because it's a fascinating story of this mine. But of course, America wasn't the only place that was polluting. This is pollution from China. Here you can see those fluids that have been used to process the ores just spewing into lakes, spewing into water courses, going into the groundwater, causing massive pollution in Chinese areas where they explore for rare earths. Now, in a lot of manufacturing, if you buy goods, the manufacturer buys his goods from different people. If he's buying cobalt, for example, he might say, well, we don't want to buy it from child labor provided cobalt production in the Democratic Republic. And there's this guide which is known as the ESG, the Environmental, Social and Governance Audit, and it gives indications to the producers of where to get more ethically sourced material. But that just doesn't exist for rare earths at the moment anyway. So there's no restriction on people actually causing pollution in their own countries, and they won't be punished because of that. So that was pollution from monazite and basastenite, but what about the ion absorption clays? Maybe because they're easier to process, they cause less pollution, for example. Well, think of this as a hill, a small hill. It's got the soil layer on top, it's got the basement rock, maybe granite down at the bottom, and then it's got this ion absorption clay layer which has been produced over many thousands, millions of years. So it's quite easy to mine it. You can just dig it up. It's clay, essentially. And in the early days, this is very common in China, by the way, only mined in China and Myanmar at the moment, I think. It's now also mined in Australia. Yeah, but the early days, it was all mined in China. and small families would go out, dig up a little bit of rare earth, put it in a wooden barrel, mix it with some reagents, get the metals out, sell them on to a supplier, etc. And then presumably just throw away the processing fluids. It was totally unregulated. That then moved on to something called heap and leach, where they build a big pile, hopefully in a concrete pit, put all the chemicals in, let it seep for several days or a few weeks, drain that off, and then sell those salts and then deal with that waste. But again, that could have been done by relatively small operations, and the amount of pollution caused was probably enormous by all of this. So everybody knew in the early days that China was having massive, massive environmental pollution problems. But in the late 2000s anyway, China began to crack down on all these very small miners to make sure that they aggregated into larger miners and to bring in environmental controls. And that had some impacts on global markets, as we'll see in a minute. But they basically trying very hard and still trying to clean up their act in China. But one thing they have done is change the method from heap and leach, and they now mine all their iron absorption clays, and they mine quite a lot, by this method, which is called in situ leaching. So instead of digging it out as a pile and putting it in a concrete bath, you just drill lots of holes in the hillside. You inject in under high pressure all these fluids, sodium bicarbonate, I think it was, and then you drill a hole at the bottom of the hill and you hope to catch everything you put in and you drain it off. But of course, all of you can see, I can see, everyone can see, it's not all going to come back. I mean, these rocks at the basement, they have cracks and joints and escape routes in them, and even if it comes out at the edge, are you going to catch it all? So it's less obvious that you're polluting, and it's got more, maybe there's a little less potential for pollution, maybe the pollution levels are less here, but it still has quite a lot of potential for pollution through this. Not only that, but it's made of clay, and as you pump in all these fluids under pressure, and including water, then those clays get hydrated, and when clays get hydrated, they expand. But when they expand, they become unstable, and when they become unstable, you get a landslide. So this is a method of creating landslides, and they do happen in these areas as well. But it's quite well regulated in China now, but because China has cut back on its small miners, it's begun to bring in a lot of rare earths from places like Myanmar, where the regulation is unknown, if it exists at all. And here's some of the people in Myanmar drilling holes in that very material to pump in their fluids. And of course, Myanmar is also in a war zone, so they're not going to be very well regulated at all. So let's summarize the environmental issues. Each mineral has its own problems. Each mine has its own problems, basically. The China Daily in 2010 reported that refining 1 ton of rare earth oxide can produce 60,000 cubic meters of waste gas containing sulfuric and hydrochloric acid, 200 cubic meters of acidic water, and 1.4 tons of radioactive waste. So, although these are green elements, their production is not very green at all. Not very, unless they're highly regulated. So you could reduce all of that, of course. You could manage all of that if you had strong regulation. But as I showed you, even in America, the regulation was pretty poor. So they produce large amounts of tailings containing naturally occurring radionuclides. So thorium and uranium are quite common in the basastenites and the monazites. So it's quite nasty material that's being polluted here as well. The environmental management's often been very poor, as I've said. Now there are less small sites, but even large sites can have their problems. And there's been much illegal and unregulated mining over the past. So all of these issues really do counter the benefits we get from rare earths and need to be borne in mind. Oh, and these ion absorption clays, of course, are used in situ with ammonium sulfate and other chemicals. So the other issue, which you'll hear about on the TV, is the economic issues. And one of those is related to monopoly production. So here you can see from 1950 all the way to 2010, the production in metric tons of rare earths globally. And you see that in the early years, well, from 1960 or so onwards, America became the dominant producer in the world. From that one single mine that I showed you the picture of, Mountain Pass Mine. And by the mid-1980s, it was dominating absolutely everything. I think at one year it produced 90% of the world's rare earths. But in the 80s, China developed a policy that it would expand its rare earth production and its rare earth export, and it began producing by many of those very small mines that I told you about before. And that put pressure on the USA production because it reduced the price and flooded the market, and also the American mine was suffering its own problems with pollution, and by 2002 it closed. And at that point, China had already become dominant before that, but then it became absolutely dominant and has dominated with 90% of the production of global rare earths. This map only goes to 2010. So rare earths are not the only commodity which has monopoly production. Let's show you a few of the others. So here you can see that South Africa dominates precious metals and platinum, that Democratic Republic of Congo dominates the cobalt production, that lithium is produced primarily in Australia, but that China dominates production of graphite, rare earth elements, and magnesium. So it's not just rare earths that China dominates. But the rare earth ones became a problem because in 2010, there was a dispute between China and Japan. So what happened was a Chinese fishing vessel entered Japanese waters and began illegally fishing, so the Japanese said. But the Chinese thought it was their waters, because they always dispute who owns the waters. And so they had a spat, and so China cut off all its supply of rare earths to the electronics industry in Japan. And overnight, that industry came to a halt. Pretty much overnight. It didn't last long, but it certainly shook the world. And this is what happened to the value of rare earths, which is the blue line. It went from less than $10,000 a ton to more than $40,000 a ton. And the production went down because China stopped exporting quite a lot of its rare earths at that time. So this had major impacts, and the world suddenly woke up to what a monopoly can mean if some country has it over other countries. And we've heard about it recently again in the news about rare earths as well. I haven't gone up to the present day disputes with America and China and Trump in this talk, but you'll be better armed to read those stories after this, hopefully. So this was a major shock to the world, major shock. And since then, other countries have woken up and they've begun to produce. So this graph now goes from 85 to 2022. And you can see now that the USA has come back into production, the Myanmar production, which I told you about earlier, but all the Myanmar production goes straight to China, so you could actually count that as part of the Chinese production. Australia is now coming online with quite a big mine called Mount Weld. Madagascar and other countries are producing small amounts of rare earths now. And if you want to look at it in 2024, the previous slide had a total of about 300,000 tons mined in a year. This slide has 400,000 tons because the production is going up year on year. And China is, a year ago was producing about 69% of the world's rare earths, but USA was now back up to 11%. So let's go back to this mine because I found this story quite fascinating. So production in this mine in America, the only mine producing rare earths then and now, I believe, although others might be coming on stream in America, began in about 1952 and increased production quite dramatically in the 60s, and it produced all the europium that was put into TV screens, and then cerium that was in cathode ray tubes, and then it began to produce gadolinium, samarium, neodymium, and dysprosium for uses in magnets, and particularly for use in the defense industries. So it was quite profitable, very profitable for many years. So let's go through the timeline. So they began in 1952. The company was called Molycorp, and they became the dominant producer from the 60s to the 80s. In 1997, it was bought by Unocal, and refining was then progressively transferred to China. As I told you earlier, they got rid of their pollution by dumping it all on China, letting them pollute themselves, and then bought the minerals back. But the pollution incidents began to mount up, and the profitability went down, and by 2002, they suspended production. It was then strangely sold to Chevron, because Unocal also had a lot of oil interests as well. I think they accidentally bought the mine. And then a new industry called New Molycorp was set up and bought from Chevron in 2008, but it's not producing any minerals at this time. But in 2010, and this is because the price shot up because China stopped exporting and the world price went up, they thought, oh, what a great opportunity, we'll put a huge amount of investment in. So they invested very highly in developing the mine, not actually mining yet. But in 2015, so we've gone now from 2010 to 2015, they haven't mined anything yet, but America, in the meantime, had gone to the World Trade Organization and complained that China was restricting supplies onto the world market. China lost and then flooded the world market with rare earths, so the price plummeted again, and the mine went out of business. It went bankrupt. But that was not the end of it. So another company called MP Minerals, which I think stands for Mountain Pass Minerals, they bought the company in 2017, but this time with an 8% stake by China. So China and America have been intimately involved in rare earth production all the way through. And they began to produce again in 2018, but still refined in China. They hadn't built the refining plants at this time. And it wasn't until 2023 that the refining came back finally to the USA. And finally in 2025, the Pentagon realized it was such a strategic mineral that they bought a 15% stake. So this is an example of how capitalism finds it very difficult to cope with somebody having a monopoly and with a complicated set of minerals like rare earths. And I'll show you another complication to that in a minute. And how it struggles back into, whereas China can just sail through and produce and control everything. So what about the future and the development of new rare earth mines? Oh, we're coming to another myth, I think. So this is the metals market, the total value of it in US billions. So it's not really that massive a market. The total value is only worth $10 billion. The total value is only worth $413 billion in 2025. But this is what Trump said. This is a direct quote from Fox News on February the 10th this year. You might want to read it. I told them, Ukraine, that I want the equivalent of 500 billion worth of rare earth. And they essentially agreed to do that, so at least we don't feel stupid. It's good English. Trump said, okay, but 500 billion is 100 years worth of the total rare earth market, most of which is produced in China. So there's absolutely no way that statement makes any sense whatsoever. But to be fair to Trump, I think what he was doing here is deliberately twisting things. So they might have talked about 500 billion worth of metals or commodities of some sort, but the word rare earth had much more resonance. So Trump didn't bother with all the rest. He just said it was all rare earth because it sounds good to the American people, and I suspect that's why. And this is a problem with things being called rare earths. If they were called lanthanides, he wouldn't have said 500 billion worth of lanthanides, would he? He wouldn't have had the same resonance. So I think that's quite an interesting statement. And then we go to Ukraine itself. This is a map produced in Soviet times. It has greenish dots on it representing rare earths, apparently, but I've read some reports which say the map was produced in Soviet times and that the Soviet geologists, when they came back at the end of an expedition, couldn't say they hadn't found anything, so they put dots on a map because nobody was going to go mine them. So who knows whether they exist or not. And in no paper I've read has it talked about mining in Ukraine for rare earths, so they may not exist at all. Who knows? Anyway, let's look at price volatility. This is the price of europium, okay, all the way from 2007 to 2024. So originally, China dominated the market. It was worth about $1,000 a kilogram. Then, during the crisis of 2010, dispute with Japan, it shot up in value, and then it plummeted. But it was used in fluorescent lamps. We don't use fluorescent lamps anymore, so its price has gone rock bottom, and it's now only worth $27 a ton. So if you want to open a mine, you can't tell your bank you've got this market which is going to go on forever, because they could look at the history of some of these and find that they have plummeted with time. So let's look at two heavy rare earths, terbium and dysprosium. Terbium's used quite a lot. It's a very important rare earth now. They have maintained their value just about. They both went up in 2010, but they haven't really gone down much. But these are not inflation adjusted, so they've really gone down with time in their value. And this peak occurs in a lot of the graphs, and I couldn't find out why for a while, but I found out today. This is due to three factors: the environmental push by China, which was cleaning up its act and therefore closing down a lot of small companies, which reduced supply. It was caused by the large increase in the amount of electric cars being built and the end of COVID. And so it was a temporary blip. All of those three have gone away now, so don't worry about the 2022 blip. So terbium is used in guidance systems for hypersonic missiles, night vision, electronic countermeasures, advanced radar, etc. It's very important. By the way, I was going to mention promethium before, because nobody was sharp-eyed enough to pull me up on the fact that when I showed that list of elements with all the colors, there were only 15 and not 17. Promethium was missing because it's radioactive, and it has a half-life of 17.7 years. But weirdly, I found out it's got a market in making pacemakers and guided missiles. And I don't know, they seem like strange bedfellows to me, but anyway. Anyone wearing a pacemaker, you've got some in you. So here's the market for neodymium, light, lanthanum light, and cerium light, three rare earths, two of which have gone down to rock bottom, and one's just about maintained its price with time. So, and these numbers were so extraordinary, I thought I'd put them on a table as well as the graph, because you can see here that cerium, it's found in huge proportions, because it's very common. But even that's gone down from $5 to $1 per kilogram. Dysprosium, one of the key elements, hasn't really gone up much over time. Europium, as I said, has plummeted in value. Lanthanum, nothing's really gone up very much apart from terbium, maybe, which has gone up a little bit. So in terms of long-term investment, and in terms of persuading the bank to lend you about $1.3 billion, which is probably what you need to open a mine, you haven't got a lot of track record to show in the increasing value of these products. And the fact that you mine maybe 7 or 8 elements from the same mine, and you can't predict the value of any one of them with great certainty. But I suppose at least we can say now that batteries are taking off, and neodymium and praseodymium are going to be really important in the future. So production in tons per year, you can see here that we produce huge amounts of cerium because it's so common in a lot of those mines that are that are exploited, and lanthanum. But a lot of the other rare earths are really not very common at all, particularly the heavy rare earths. Look how little amount of heavy rare earths are mined per year compared to the light rare earths. So if it doesn't say heavy, it means light. So heavy rare earths, if we need to use them in large numbers, then we're not producing very much at the moment. So I'm just going to deviate into mining geology. How am I doing on time? Have I got 10 minutes left? 5 minutes left? Yeah.
50 minutes.
Oh, okay, perfect. So I'm going to train you now as mining geologists. So if you go, if you buy a plot of land, large plot of land where you hope to build a mine, you get a license to build a mine. You've then got to persuade the bank to lend you a huge amount of money to build that mine. So you've got to prove you've got enough material to be worth the value of that investment. So you drill a few holes, you analyze what's in them, and when you've got enough confidence that you've got a big enough patch to be profitable, you can then go to the bank. So that's known as proven reserves, what you absolutely know is there. You know 100% you've got this amount of ore of this percentage production in the rock, and you can go to the bank with that number. But along the way, you'll have these other three on the left. You have inferred, which means we guess there's going to be some here, basically, very little information. And then you get some information, and you indicate you're probably going to have this amount of resource, and then you actually measure the resource, and that becomes the proven reserve. So these are just levels of geological knowledge and confidence. It's all very well structured in the mining industry. And there's a code of standards where you have to show how you've done the measuring, what you've measured, everything about it to prove that you've got inferred, not indicated, not measured, or vice versa. But then proven reserves can go up and down. So one thing, of course, you mine them away each year, so the proven reserve should be going down each year. But you might find that some of the indicated reserves, you get more information and you say, oh yes, that we indicated it was that much, but it's actually now measured and it is that much, so it goes into your reserves. But then if the price of the metal goes down, then the amount of reserves goes down as well, because you can't mine it profitably anymore. So you have this thing called a cut-off grade. So you say, this mine's profitable for all the amount of that metal above 2%, let's say. 2% of the rock is that metal, therefore it's profitable. But, and that's profitable based on how much it costs to mine it, how much it costs to process it, whatever the environmental conditions are at the time, cost of labor, cost of infrastructure, etc., a whole range of parameters. But if they change, for example, the government brings in a new environmental law that puts up your prices, then your profitability goes down and your proven reserves probably go down, and you know where you're heading, so you have to quickly see if you can find some more reserve over here. So, well, wait a minute. So the two important words from here, on the left it's resources, and on the right it's reserves. So reserves are known things on which the mine is actually running, and resources are things which you're working on to try and turn into reserves when you get enough information. Reserves are part of resources, but not the total part. So this is reserves, and this data comes from the USGS, United States Geological Survey, and is very honest and factual data. So the total reserves, which is the total properly known amount of rare earth in the world in these countries is on this map, is on this chart. And the annual demand, remember, is about 403,000 tons. So we've got about 40 million tons, and we're using about 500,000 tons a year. So we've got plenty of rare earth to be going on with at the moment. And the other interesting thing on this slide is Greenland pops in. And now you know why Greenland's in there. No, not why Greenland's in there, why certain countries are interested in Greenland, probably. Yeah, maybe the case. It's not being mined yet, but it's got some pretty good reserves in Greenland. So this graph, nearly the final graph, This is the resources graph now, okay? So this includes the reserves, which was in the previous graph, but it's all the mines that are projected to begin in the next few years. Now, this is a debatable number because I got this from one paper, or Geology Reviews, and if somebody else wrote a paper, they might have a different opinion about what's coming on stream and what isn't. But these are meant to be the mines that are progressing towards production, combined with the mines that are already producing. So you see in the previous slide, China was dominant. In this slide, China is dominant. So China's always going to be dominant in rare earths. It just has the right geology to remain dominant. But Australia is coming up very fast. It's got lots of rare earths in Australia. And again, we've got Greenland on here with quite a lot of resources potentially in Greenland. USA has got a little bit, but it's got enough for its own purposes probably, but it doesn't have as much as the rest at the moment. But what's also marked on here is the proportion of heavy rare earths, intermediate and light rare earths. In fact, the graph is made up of all the individual mines, but you can't see how the columns divide up because it's dominated by a small number of large mines. So Greenland actually has quite a lot of the heavy rare earth, which, as I've explained as we've gone through the talk, is really the rare one and the one that's potentially going to be more in demand than the others. Intermediate rare earth means it's got some heavy and some light rare earth elements in it, so Australia's quite well placed as well. But China's, dominates the numbers in all these graphs. So that's 276 million tons of rare earth, and if we're using it at 500,000 tons a year, there's not a major problem really going forward, except potentially for the heavy rare earths. And that was going to be the end of the talk, and I looked on the web a couple of days ago, and I found this. In August 2025, Victory Metals in Australia announced North Stanmore. If you want to do some investment, don't say I told you so, but and don't invest any more than you can lose. But this seems to be quite a massive discovery, actually. 320 million tons of rare earth, but this is iron absorption clay, so it's very low percentage rare earth in the ore, and it's been JORC compliant, so it's gone through some sort of test of the validity of the data, and it has indicated and inferred resources. It doesn't have any proven resources yet because they're still doing the drilling, but things are looking pretty good. 83% of their mine will be heavy rare earths, and it's not going to be so expensive to process because it's this iron absorption clay. So potentially that will do a massive rebalance and make Australia one of the big rare earth countries in the world. Maybe too far away for America to have its eyes on at the moment, I'm not sure. So let's conclude. Rare earths fall into light and heavy, of which light rare earths are not really rare, but heavy rare earths have a much more limited supply. China's been and will remain dominant, but other nations are now beginning to exploit resources. Demand will continue to grow quite dramatically due to increased use in electronics, renewable energy, adoption of EVs, etc. They're vital components of permanent magnets, and they're required in the production of motors and generators. They're increasingly important for military and defense sectors, and they're part of the green revolution, but their exploitation can cause this severe pollution problem that I discussed. Oh, that was the last one. Yeah. Okay, so there we go. Thank you.